I feel like we've all had that one roommate or maybe a sibling who just completely takes over the
Oh,
house.
absolutely. The one who just sprawls out everywhere.
Right. They take up all the space, they control the thermostat, leave their stuff everywhere, and basically everyone else in the house just has to, adapt to their rules.
The whole environment just sort of bends around their gravity. I mean, literally and figuratively.
Exactly. And when you look at our solar system, we have this ultimate space hogging roommate, which is Jupiter. I mean, it is the undisputed heavyweight champion of our cosmic neighborhood.
Yeah, it really is.
But what's truly mind-bending, and really the mission for this deep dive today, is understanding why this incredibly hostile, massive planet is acting as the anchor for a miniature solar system of moons that surprisingly actually hold our biggest hopes for finding alien life.
It's a brilliant contradiction, really. I mean, the most dangerous environment imaginable is somehow generating the exact conditions needed for biology.
And for you listening to really grasp how it does that, we have to understand its sheer incomprehensible scale. Jupiter is about 11 times Earth's diameter.
Right.
It has more than 300 times Earth's mass. Like, if you took every single other planet in our solar system, Mars, Venus, Saturn, all of them, and mashed them into one giant ball, Jupiter would still be more than twice as massive as all of them combined.
It is the dominant object in the solar system, second only to the sun itself.
Oh.
And, well, it's made of completely different material than a rocky planet like Earth. It's overwhelmingly hydrogen and helium.
Which is essentially the exact same makeup as the sun. So I always hear people call Jupiter a failed star, but I struggle with that term a bit. Is it actually on the verge of bursting into a star, or is that just an exaggeration?
It's a bit of both, but mostly an exaggeration. It's not a near miss. You shouldn't picture Jupiter as being just a few pounds shy of lighting up the night sky.
Okay, so it's not like adding one more asteroid will ignite it.
No, not at all. You would need somewhere around 80 times Jupiter's current mass before the pressure and temperature deep inside its core could actually ignite hydrogen fusion. So it falls very short of being a star.
Got it. Okay, so it's not a star. But it actually radiates more heat out into space than it receives from the sun. If it's not doing fusion, how is it generating that much heat?
Right, so that's through its own gravity.
Yeah.
Because it has so much mass, the entire planet is constantly pulling inward on itself.
Like it's shrinking.
Essentially, yes. That immense, slow gravitational contraction causes this continuous squeezing effect. And that physical squeezing generates internal heat.
Which brings up a slightly naive question, but I think it's what everyone pictures when they hear the term gas giant.
Sure.
If there's absolutely no hard surface to land on, if I took a bowling ball and just dropped it into Jupiter, does it just fall forever until it eventually melts?
Actually, that is the perfect way to picture it, because a planet without a surface is entirely counterintuitive to how we experience the world.
Right, we're used to hitting the ground.
Exactly. If you drop that bowling ball, there's no splat. It wouldn't hit a hard ground. As it descends through the atmosphere, the gas around it simply grows denser and denser and hotter.
No clear boundary at all.
None. Eventually, without any clear line to cross, the gas becomes so incredibly dense that it transitions and begins to behave as a liquid.
Wow.
So your bowling ball wouldn't plonk onto a surface, it would just sink into an increasingly thick, boiling hot fluid.
That is deeply unsettling to think about.
Oh, but it gets stranger. If you follow that bowling ball deeper still, the pressure becomes so extreme that we reach one of the most fascinating physical states in the universe, which is metallic hydrogen.
Now, wait, metallic hydrogen sounds like a complete oxymoron. Hydrogen is lightweight gas. How does it become a metal?
It's all about that crushing pressure we were just talking about. Down in the extreme depths of Jupiter, the weight of the atmosphere above is so intense that the hydrogen atoms are violently squeezed together. The pressure actually strips the electrons away from the hydrogen nuclei.
Meaning the electrons are just freely floating around, like how they behave in a copper wire.
Precisely. Because those electrons are free to move, that ocean of hydrogen suddenly conducts electricity, which, is the defining characteristic of a metal.
Oh, I see.
So you have this vast, swirling, liquid ocean of electrically conducting metallic hydrogen just churning away inside the planet. And that massive conducting ocean is almost certainly what generates Jupiter's colossal magnetic field.
And the scale of that magnetic field is just absurd. It's the largest structure in the solar system outside of the sun's own magnetic influence.
It really is.
Like if you were standing outside at night, and we could somehow see Jupiter's magnetic field from Earth with our naked eyes,
Yeah.
it would appear several times wider than the full moon.
Which is staggering to think about. I mean, Jupiter is hundreds of millions of miles away, yet its magnetic footprint would absolutely dominate our night sky.
So this liquid metallic hydrogen is the engine driving this magnetic monster. But all that internal heat and energy also drives some truly wild weather up in the atmosphere. Oh, incredibly wild.
Because despite being this enormous heavy beast, Jupiter rotates incredibly fast.
Oh.
A full day there is under 10 hours.
And that rapid rotation has massive physical consequences. Imagine spinning a balloon made of liquid. It spins so fast that the planet physically bulges at the equator and flattens out at the poles.
It's not even a perfect sphere.
Right. And that intense spin takes all of its weather systems and stretches them out horizontally into those famous, beautiful stripes of clouds we always see in photos.
And those stripes are moving in opposite directions, creating sheer chaos where they meet, which brings to mind the Great Red Spot.
Ah, yes.
It's categorized as an anticyclone. But I need you to explain this because on Earth, when the weather reporter says we have a high-pressure system coming in, that usually means clear blue skies and calm weather. How does high pressure on Jupiter create a raging, violent storm?
That's a great distinction to make. So an anticyclone is a weather system where winds circulate around a central region of high atmospheric pressure.
On Earth, our atmosphere is relatively thin, and high pressure gently pushes air downward, which clears out clouds. But Jupiter's atmosphere is immensely deep and just churning with internal heat.
So it reacts differently.
Very differently. When a high-pressure zone forms there, it creates a massive, swirling vortex. The pressure pushes outward, forcing the winds to race around it at hundreds of miles per hour. It's less of a gentle clearing system and more of a heavily pressurized atmospheric engine.
And this storm is large enough to swallow the Earth whole. It's been observed for at least a century and a half, maybe much longer based on historical astronomy records, though it has been measurably shrinking and getting rounder in recent decades.
Yeah, the longevity is what usually surprises people the most. Like, how does a single storm last for centuries?
Well, the best way I can picture why it lasts so long is to think of a spinning top on a perfectly frictionless floor.
That's a good analogy.
Down here on Earth, a hurricane gets its energy from the warm ocean, but eventually it hits a landmass. That land creates friction, cuts off its fuel, and breaks the storm apart. But on Jupiter, there is no land surface.
Right, no solid ground.
The floor is frictionless, there's nothing to slow the momentum down, so this storm just keeps spinning, continuously fed by the neighboring jet streams for hundreds of years.
That's exactly the mechanism. Without a solid surface to disrupt the fluid dynamics, that momentum is preserved almost indefinitely.
And as much as we think we understand it, we are still discovering entirely new things under those clouds. Like the Juno spacecraft arrived at Jupiter in 2016, and it delivered data that completely upended our models.
It really did.
For instance, before Juno, the assumption was that Jupiter probably had a compact, solid core of rock and ice at the very center. But Juno revealed the core is actually fuzzy or diluted.
Yes, fuzzy is the exact term planetary scientists are using right now.
What exactly is a fuzzy core? Like, how does rock and ice become fuzzy?
Well, it means there isn't a sharp boundary where the metallic hydrogen ends and a solid rock begins. Instead, the heavy elements of rock and ice are dissolved and blended into the liquid metallic hydrogen above them.
So it's just this huge smeared out transitional zone.
Exactly.
But how does that even happen?
The most plausible explanation currently points to a major head-on collision very early in Jupiter's history. A massive planetary body, maybe 10 times the mass of Earth, could have slammed into Jupiter.
Wow.
Right, and it essentially shattered the original solid core and stirred it up like a spoon in a teacup, mixing those heavy elements permanently into the fluid layers above.
That paints such a violent picture of the early solar system. And Juno didn't just look deep inside, it looked at the poles. It found these bizarre, highly stable geometric clusters of enormous cyclones, just perfectly arranged in geometric patterns like an octagon of storms surrounding one central storm.
It looks completely artificial when you first see it, but it's purely fluid dynamics.
How does a chaotic atmosphere build perfect geometry?
It really comes down to the physics of vortices. When you have multiple massive storms driven to the poles by Jupiter's rotation, they start to repel each other.
So they push away.
Yes, and they find a state of equilibrium where they are close enough to interact but push against one another just enough to lock into these stable, crystalline patterns. It's a delicate balance of fluid mechanics that we rarely ever see on such a colossal scale.
It's alien in every sense of the word. But if Jupiter's gravity is strong enough to dictate perfect geometry at its poles, it's really not surprising that its gravity reaches out and dictates the architecture of the entire solar
Well,
system.
sure. It is the ultimate gravitational anchor.
Right. It's shaped exactly where material could accumulate when the planets were first forming. But there's a specific narrative I want to challenge here. I always hear Jupiter called our cosmic shield. The idea that its massive gravity deflects or captures comets and asteroids that would otherwise wipe out the inner planets, like Earth.
Yeah, it's a very common idea.
But the research also notes that Jupiter's gravity perturbs objects inward. So, is Jupiter our noble protector taking hits for us? Or is it a sniper occasionally throwing rocks at our heads?
That is the exact debate happening in astronomy today. The cosmic shield narrative is highly popular, but it's considered far too simplistic now.
Because it does both.
Right. It's true that Jupiter's gravity sweeps up a lot of dangerous debris. I mean, we actually watched a comet called Shoemaker-Levy 9 smash into it in the 1990s.
I remember seeing pictures of that.
Yeah, it was incredible.
Yeah.
But at the same time, its gravity destabilizes the orbits of other objects, nudging them out of safe paths and sending them hurtling toward the inner solar system.
So it really is a two-way street.
Exactly. The net effect, whether Jupiter has saved Earth from more impacts than it has actively caused, is hotly debated. But regardless of whether it's a shield or a sniper, its absolute control over the layout of the solar system is undeniable.
And if Jupiter's gravity is strong enough to toss comets across the solar system, what does it do to the objects trapped right next to it? Which brings us to the second half of our mission today.
The moons.
The Jovian system.
Yeah, Jupiter has over 90 confirmed moons, but we are focusing on the big four: Io, Europa, Ganymede, and Callisto.
The famous Galilean moons.
Right, named because Galileo spotted them in 1610 with a modest early telescope. And you really have to appreciate the historical weight of that moment. He looks at this primitive tube of glass, sees 4 dots moving around Jupiter, and realizes they're orbiting the planet, not Earth.
It was a massive realization.
It was direct, undeniable evidence that the Earth was not the center of all celestial motion, a total paradigm shift.
It was essentially the dawn of modern astronomy. He realized he wasn't just looking at a planet, but an entirely distinct planetary system.
And when you zoom in on the closest of those 4 moons, Io, you see just how violently that system operates. Io is the most volcanically active body we know of. Visually, it is this lurid yellow-orange color because it is coated in sulfur compounds. It looks a bit like a moldy pizza.
It really does. It has hundreds of active volcanoes shooting plumes hundreds of kilometers straight up into space. And uniquely, there are 0 impact craters on its surface.
Which is very telling. In space, if a surface has no craters, it means it is extremely young.
Because it's constantly paving over itself.
Yes. The volcanoes are erupting so constantly that the lava and sulfur repave the surface faster than meteor craters can even accumulate. It is just a world of endless geological violence.
But here's what I find confusing about that. Io is hundreds of millions of miles away from the sun. It should be a frozen, dead rock. Where is it getting the heat to melt its entire interior?
This brings us to the defining scientific concept for the entire Jupiter-Moon system, which is tidal heating.
So how does tidal heating actually work?
Well, it's all about gravity and geometry. Io's orbit around Jupiter is not a perfect circle. It's slightly elliptical or oval-shaped. And this is partly because the gravity of the other nearby moons tugs on Io, preventing its orbit from settling into a perfect circle. Because the orbit is elliptical, Io's physical distance from Jupiter is constantly changing. Sometimes it's a bit closer, sometimes a bit further away.
Meaning the strength of Jupiter's gravitational pull on Io is constantly increasing and decreasing as it moves.
Precisely. As it orbits, that immense gravity stretches and squeezes the solid rock of Io by varying amounts.
Oh, wow. Just squeezing solid rock.
Yeah. This continuous, relentless physical flexing generates massive amounts of internal heat through friction. The research provides a perfect everyday analogy. If you take a solid metal paperclip and rapidly bend it back and forth in your hands, the metal gets hot.
That makes perfect sense. I keep picturing Io as this giant sulfur-flavored stress ball being endlessly squeezed and released by Jupiter's massive gravitational hand. All that kneading creates friction. The friction creates heat, and that energy has to go somewhere.
Yeah, exactly.
So it bursts out as volcanoes.
A very vivid way to picture it, but scientifically spot on. The friction melts the rock itself.
So if tidal heating causes literal fire and endless volcanoes on the closest moon, What does that exact same squeezing do to the next moon out? Because the second Galilean moon is Europa, and Europa happens to be entirely covered in ice.
And this is where the story shifts from dramatic, fiery violence to the profound potential for alien biology.
Europa is slightly smaller than our own moon. Its surface is essentially water ice, and it is one of the smoothest objects in the solar system. Very few craters, but it is crisscrossed by these long, dark, mysterious fractures.
Yikes.
And again, few craters means a young surface that is actively being renewed.
Something is constantly cracking and resurfacing that ice, and all the evidence points to a stunning reality beneath that crust, a global subsurface ocean of liquid salt water.
Hiding under an ice shell that is estimated to be 10 to 30 kilometers thick. And the volume of water we are talking about is staggering. Europa is smaller than our moon, but that subsurface ocean holds roughly twice the amount of liquid water as all of Earth's oceans combined.
It is arguably the most significant body of water in the solar system.
But wait, we've never drilled into it. It's hidden under 30 kilometers of ice, 400 million miles away. How can we possibly know it's a salty liquid ocean? How do we know it's not just solid ice all the way down?
It's an absolutely brilliant piece of scientific deduction, and the strongest proof is actually magnetic. Remember Jupiter's massive spinning magnetic field we talked about earlier?
The one wider than the full moon.
Right. As Europa orbits through that invisible magnetic field, Jupiter's field actually induces a secondary magnetic field inside Europa.
Oh, really?
Yes, and the specific way Europa's magnetic field responds and fluctuates tells us exactly what's inside. It requires there to be a global, highly conductive layer just beneath the surface.
And solid ice doesn't conduct electricity.
Exactly. Solid ice is a terrible conductor, but liquid salt water is a fantastic conductor. When you combine that magnetic signature with the visually fractured mobile ice surface, plus observations that look very much like water vapor plumes venting into space, the case for a vast liquid saltwater ocean is incredibly strong.
So we have a massive salty ocean, kept liquid in the freezing depths of space by that same tidal heating we saw in Io.
Yes, exactly.
It's just a gentler version of the stress ball effect. The squeezing isn't strong enough to melt rock into lava, but it is strong enough to melt ice into an ocean.
Yes. The orbital flexing warms the interior just enough to maintain that liquid state beneath the insulating ice shell. And this leads us to the most exciting concept of this entire deep dive: chemosynthesis.
This is the biology part.
Right. On Earth, we are heavily biased toward photosynthesis.
Yeah.
We think of life as depending on energy from the sun. Plants use sunlight, animals eat plants, and so on.
Sure.
But deep down in Earth's own oceans, thousands of feet below the surface in total pitch-black darkness, we find entire complex ecosystems thriving around hydrothermal vents.
Like underwater volcanoes.
Exactly. Where hot, mineral-rich water from the planet's interior meets the cold ocean water, life flourishes without a single drop of sunlight. The organisms there survive on chemosynthesis. They extract their vital energy directly from the chemical reactions happening at those vents.
And we think Europa has those vents.
Well, think about the ingredients. Europa has a massive liquid ocean sitting directly on top of a rocky seafloor. That rocky seafloor is being actively kneaded and warmed by Jupiter's tidal heating. It is highly plausible that Europa has active hydrothermal vents on its ocean floor.
It is a complete paradigm shift. It's honestly amazing to me. We spend so much time and billions of dollars looking at Mars, hoping to maybe find the fossilized remains of a dried-up microbe in the red dusts.
Right, looking for past life.
But it turns out the absolute prime real estate for living, breathing alien life in our solar system might be in permanent, pitch-black darkness under 20 kilometers of solid ice. Europa is genuinely regarded as a top candidate for life, arguably ahead of Mars.
It forces us to completely redefine our understanding of where life can exist. It proves that a planet doesn't need to be in the Goldilocks zone of a star to be habitable. It just needs a heat source, liquid water, and the right chemistry.
So as we move even further out from Jupiter, rounding out the Galilean family, we start to see that tidal heating effect fade away. But it leaves behind a very different world.
We do. The third moon out is Ganymede, which is a record breaker. It is the largest moon in the solar system. It's physically larger than the planet Mercury.
And it generates its own magnetic field, right?
It is the only moon we know of that generates its own internal magnetic field.
Why does that matter so much?
Because a magnetic field requires a churning, liquid conductive core. So Ganymede almost certainly has a liquid iron core deep inside. And it also has a subsurface ocean. But because it is further away from Jupiter, it experiences less tidal heating than Europa.
So the ice freezes deeper.
Precisely. The data suggests Ganymede's ocean is buried much deeper beneath a much thicker ice crust. The heat isn't strong enough to keep the water close to the surface.
And finally, we reach the outermost of the big four, Callisto. And Callisto is basically the exact opposite of Io. It is heavily cratered and geologically dead.
It's essentially an ancient relic. Because it orbits the furthest out, it largely escaped the intense, violent gravitational squeezing that drives Io and Europa.
So it just kind of sits there.
Yeah, it just sits there, preserving the ancient, battered history of the early solar system. Though, incredibly, even Callisto might hide a deep, frozen ocean of its own.
So when you step back and look at this single planetary system, you have a moon being continuously torn apart by volcanoes, a moon with a hidden ocean that might harbor life, a moon larger than a planet with its own iron core, and an ancient, battered relic, all of them anchored by this massive churning gas giant.
It's an incredibly diverse neighborhood.
So naturally, for you listening, the question is, what comes next? Are we going to look closer?
Humanity is absolutely heading back. NASA recently launched the Europa Clipper mission. It's designed to make repeated, incredibly close flybys of Europa.
That's exciting.
It won't be looking for life directly, but it will map the ice shell in extreme detail, characterize the ocean below, and officially assess its habitability.
And the European Space Agency has a mission called JUICE, the Jupiter Icy Moons Explorer, which is going to focus heavily on Ganymede, eventually entering orbit right around it. But this brings up a massive point of frustration for me. If we know Europa has a massive ocean, and we strongly suspect it has hydrothermal vents, why are we just flying by? Why aren't we bringing a drill right now?
It's a completely fair question. But we really have to appreciate the staggering technical realities. Neither of these missions will land, and neither will drill. Think about the logistics. Drilling through 20 kilometers of rock-hard ice is profoundly difficult to do here on Earth, even with a human crew standing right there and unlimited power.
And here we are talking about doing it autonomously.
Right. You are trying to engineer an autonomous robotic drill to melt or bore through miles of alien ice in an incredibly intense radiation environment 400 million miles away from the sun, where a single communication signal takes nearly an hour just to travel back and forth.
That's a lot of hurdles.
If the drill gets stuck, a human can't fix it. It's a monumental engineering challenge that is, frankly, a problem for a future generation of missions.
Fair enough. It's easy to look at an animation on a screen and forget we are trying to thread a needle millions of miles away in the dark. But still, within the next decade, we are going to know considerably more about this tidal warmed ocean.
We are going to have a much clearer picture of whether our cosmic backyard hosts an environment truly capable of supporting biology.
So let's pull all of this together. We started with this gargantuan gas giant, hundreds of times the mass of Earth, radiating its own heat, churning with liquid metallic hydrogen, sporting geometric polar storms, and a fuzzy core from an ancient collision.
And we discovered that its immense gravity doesn't just dictate where planets form, it violently needs its closest moons, generating the friction and heat required to melt ice and create vast, hidden oceans of liquid water.
It really changes how you experience the night sky. The next time you look up on a clear night and spot Jupiter and it's very bright, you can't miss it. Remember, you aren't just looking at a dot of light or even just a planet. You are looking at a dynamic, violent, incredibly watery mini solar system all its own.
And if we connect all this to a bigger picture, it raises a truly profound question. For a century, we have been conditioned to think that life requires a planet exactly like Earth, a rock with a surface ocean, bathed in warm sunlight.
The Goldilocks zone.
Right. But if the most promising place for life in our solar system is actually found in pitch darkness, under 20 kilometers of ice, kept warm not by a star, but by the gravitational squeezing of a gas giant, well, what if that is how life usually exists in the universe?
Oh, wow. I never thought about it like that.
What if rocky planets with surface oceans and warm sunlight are actually the rare, weird outliers? What if the universe is actually teeming with life, but it's entirely hidden away inside icy moons orbiting giant planets?
That is an incredible thought to leave on. It turns out that giant space-hogging roommate who dictates all the rules for the rest of the house, they might actually be the one hosting the most interesting party in the entire neighborhood. Think about that the next time you look up at the stars.